Oh, and I fixed the 10.3. Hello and welcome back to Calculus 2, section 10.4 on the whole shopping list of tests, right? We do divergence test, we do the integral test, and then we do the P-series test. I did say this 5,000 times before, so here it is, 5,001. You are memorizing these tests. It's the only way to do these things. So by the time you're done with the chapter 10, this paper will be something that you know by heart. Each problem has a converge or diverge as an answer. And now, out of the 10 tests that we use to compute or check for convergence of series, we are going to start with the divergence test for today, the first. So divergence test. And this one is extremely simple and then kind of dangerous, so be careful. This is the only test that is going to look at the sequence and infer stuff about series. And you have to be very careful about that because it works only in this setting. So, if the sequence diverges, series will diverge. Because divergent sequence goes to infinity, and when you start adding all of those numbers, it clearly has to go to infinity again, right? It is the first line. So, here is the test. Summation of an, you can start at any value. You can start at 0, can start at 1, can start at 7, doesn't matter. So, the series an diverges if the limit as n goes to infinity of an is not 0. That's it. Now we know that this piece over here is testing for convergence or divergence of sequences. And we see that if it converges to anything else other than 0, we're going to have a divergent series. I'm not sure in which color and how many boxes I need to put around the statement that this cannot show the convergence. Hence the name divergence test, right? If you look at the paper that you have, you see that the convergence box is empty, right? Convergence box is empty. So, here in blood, this test cannot test for convergence under any circumstances. This test is not to be used. But now, this is one of the easiest tests. Yeah, sure, geometric, you just look at it and you know. But this is the test that you should try first on every problem you see in this chapter. Remember how you see the derivative and you say, okay, is this the product rule? Is this a quotient rule? Is this the, right? Or you take a look at the integral and you first want to see, oh, is this a basic u sub? Right? There is always something that it's main and first to check, right? For integration, why would you go and break your head trying to do trig sub if the u sub works, right? U sub is much easier and faster than trig sub. So, when you have integrals, which is your exam is coming up, right, next week, the first method that you are going to try on every problem is going to be basic calc 1 u sub, because it has to work somewhere or on multiple spots on this exam coming up. So you try u sub first. That is the rule of integration. And then you go with the more exotic methods, the ones that take time, right, and develop carpal tunnel. For derivatives, that's chain rule, right? If the derivative is not basic, most likely it's going to be chain rule. And then you have all the other stuff, product, quotient, and blah, blah, blah. For sequences and series, but for series, you have 10 tests. The first test you check every time is the divergence test, because it takes literally 2 seconds to try it, because you are only taking a limit of a sequence. So it take you 2 seconds to try this test, and then you just go and if that doesn't work, you go and pass. So when do you have to move and look at other 9 tests? You have to move to other 9 tests if you get that the limit is equal to 0. So I'm going to write that in blood as well. If we get limit an equal to 0, as n goes to infinity, we must use one of the other 9 tests. That's it. So, if the limit is not 0, immediately series diverges by divergence test, and you're done. If the limit is 0, you have to use something else. This test cannot show convergence. So now what do I have? I have series of 1 over 2 to the n, starting at 0, going to infinity. You say, all right, let me try divergence test because that Serbian guy said so. So limit 1 over 2 to the n as n goes to infinity. You got 0. You got 0. Walk away. All right? Walk away. Now, the divergence test failed. Divergence test failed because we got 0. So now what? Right? Well, you have to go and look at your sheet, right, and figure out what other test you can use to solve this problem. And that would be very good. So you would use geometric series test because the divergence test failed. So you will go and you will say, by geometric series test, we have r equals to 1/2, smaller than 1, converges by geometric series. Right? And that's it. You don't get to claim convergence by a test that cannot detect convergence. So don't play with fire, right? Now, let's say you also have, well, let's do this. Say you have 3 to the n, 0 to infinity. Right? You have 3 to the n. So now what you do? You try divergence again. Because you should always try divergence first. And look what you got. You got infinity. This satisfies our test up there. Because your limit is not 0. In this case, your limit is infinity. So because your limit is infinity, you will say diverges by, and you can either put divergence test or nth term test. I'll understand either way. Your book is calling it divergence. This paper is calling it nth term. Whatever you want, right? So diverges by dt, divergence test. Is there another way to solve this problem? Yeah. Geometric. This is a geometric one, right? What's my r? 3. And 3 is bigger than 1, so it's in the divergence, right? So we can solve this problem also by geometric, but again, there is always that one thing when you learn derivatives, when you learn integrals, when you learn now series, there is always that one method, one thing that it's, used most of the time. In this case, divergence is the key, right? You take every problem you see on exam, every problem you see on a homework lab, divergence first, because that knocks out, right? You'll see integral test. Takes a page, right? And why would you go through that if you can knock out this problem in a line, right? One line. Okay, let's take a look at this. Summation of 1 plus 1 over n to the n from 1 to infinity. What do we have? Right? You're looking at this. Is this geometric? No, it's not. Right? Because 1 plus 1 over n is not a 2 or a 3 or something. So you don't have your r. So you can't do that. But let's try divergence test. Limit n goes to infinity of 1 plus 1 over n to the n. What happened? Nope. 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 Nope.
Undefined.
Nope.
Zero?
Nope. So,
Negative 1 over 12.
negative 1 over 12? Nope.
Pi over 12.
Pi over 12? No.
Clearly no.
E, thank you very much.
Why did you say 1 first?
All right. Now,
Oh, I get it. I forgot that's what I used to write.
It doesn't happen very often.
yeah.
Yeah, and I watched a video about this.
Guys, this is your definition for number E. This is the definition for number E. This is the one that you memorize so you don't have to crank L'Hopital's rule on it for 7 hours.
We did not remember this. We remembered 1 over 1 plus x squared. Should we remember this now?
it helps life. All right. So now, is this 0? No, it's E. Right? So, diverges by divergence test. That's what it is. It diverges by divergence test because the limit is not 0. And that's the story of divergence test. You take a look at your series, you take the sequence AN, and you put that sequence into the over there, and you go. All right. Let's open the gates of hell. Lock the doors. Integral test. Line 6 on your sheet. Please observe that right under the integral there are some conditions on f. F is continuous, f is decreasing, and f is positive. Okay, good. Well, before you get to do integral test, you have to write these 3 proofs, and then when these 3 proofs pass, then you get to transfer your discrete function 1 over n, your discrete function f of n into a continuous function f of x, and then you can integrate. And guess which integral is in question? Of course, it's the type 1 improper integral. And you can have any integration technique within. So this can drag out for a very, very long time. So now, remember how I asked you to retire your common sense, right, and just follow the sheet? What do you think is happening with the series summation 1 over n from 1 to infinity? Would that converge or diverge? Right, just by looking at it. Right, the common sense is pretty much always going to give us the wrong answer, right? Because many of you, myself included when I was a student, we would all love to see this converge because the sequence 1 over n converges. But no, this one is a divergent series. So let's get there. How I'm going to get there? I'm going to define the integral test. So, we have summation an. This is your standard 1 to infinity, 0 to infinity, 10 to infinity, whatever. We can start anywhere. Remember, only geometric series are sensitive, right? Only geometric series are asking for 0. The other ones, they don't care, right? They're not sensitive in that way. So we have 1 to infinity an. And what I would like to do is I would like to do the integral instead of the sum. Because what is integral? Well, it is a sum, right? You should know that from chapter 5 in Calc 1 that integral is a Riemann sum. So there should be some way to jump between two worlds. Now, the an world is a discrete function, just dots, and we really can't calculate area under dots because there is no line to kind of cut off and block off that area. You all have dots and the area just leaks all around the dots, so you don't get to do integration. However, what we noticed when we did our sequences is that if you have, let's say, 1 over n and you have 1 over x, the graph is the same, right? Except one is dots and one is straight line. So now, to define this integral test, this is what I want to do. I want to transform this discrete function an into a continuous function f of x. And it's going to look the same, I'm just replacing n's by x's. Now, in order for that to hold, 3 conditions that are listed in the first box under the word integral, those 3 conditions have to hold. If any one of those fails, you cannot do integral test. So, what are the, yes?
You have another sheet?
Yes, I do. Another sheet, that will be $25. Yes, we accept yen. All right, so what do we have? We have 3 conditions. Check. Number 1, continuous. Continuous. Number 2, positive. Number 3, decreasing. So decreasing, and if these 3 conditions hold, so if it passes all of these conditions, then you can take your an and transform that into f of x, and then here is the test. Finally, here is the test. It says integral from 1 to infinity of f of x dx and summation from 1 to infinity of an. Well, I should have said check these 3 conditions. If they pass, then the integral and the series both converge or both diverge. So they share the same fate. And that's the test. So now let's do the first example, and that is going to be summation of 1 over n. From 1 to infinity. Now, as I said, right, we would love this to converge, but it won't. Which is why we have to do these tests.
Well, why does that logic not work? What is...
It's just the evil section. I mean the chapter. That's the best answer I can give you. I asked 5 times so far to retire common sense in this because I know where I failed. Right? So it is very simple. Retire common sense and just learn the sheet. That's all advice I can give, and you are now, as adults, welcome to do whatever the hell you want. I know how I got not to have a good time when I was learning this, right? Because I tried to reason with it and I tried to use common sense and I messed up pretty much every single time. I'm sorry, but it can be done differently. Okay, so what do I have, guys? I have the an, which is 1 over n, and I know that I would love to transform that into 1 over x. Now, in order for all of this stuff to work, I have to go and solve those 3. I have to show those 3 conditions. So I need, number 1, I need 1 over x to be continuous. Number 1, continuity. Is it continuous? Well, is it continuous? The answer is 1 over x is not continuous, but we are on the interval 1 to infinity, so it is continuous, right? So look, you have a graph for 1 over x, and it clearly has a vertical asymptote at 0. But please pay attention here. The domain starts at 1. When I do the integral later on, it's going to be 1 to infinity. So I don't care about the state of the function prior to 1. The only thing I care about is 1 to positive infinity. And that is perfectly continuous. So is 1 over x continuous? Yes. 1 over x is continuous on 1 to infinity. So we have to worry about these smaller domains. The next question is it positive? Now, you look at the graph, because, right, this is one of the easy cases. You know the graph, so just look at it with your eyes. Is it positive? Yes, because graph is always above x-axis. All of the y values are positive. That's what it means. Is it positive? Meaning, are the y values for each x from 1 to infinity, are all of the y values positive? Yes, because it's above x-axis. So, yes, because all y values are positive. So that's what we mean by the positive. And finally, decreasing. Is it decreasing? Well, you use your eyes again, look at it and say yes, right? It's going down. As you go to the right, it's going down. So yes, because there you go. But there is much better way to do this, and that is the first derivative, right? Remember that if we take the derivative, if the derivative is negative everywhere, it's decreasing. If the derivative is positive, it's increasing. So we can also do the first derivative, and we know that f prime of x in this case would be negative 1 over x squared. Now, would you all agree that the x squared is always positive? So 1 divided by x squared will always be positive, and you have a negative in front. So the other way to explain this is to show that derivative, first derivative, So because you find the derivative and then you say yes, because f prime of x is always negative on 1 to infinity. Now I have completed all three. I have a yes, I have a yes on continuous, yes on positive, yes on decreasing. So these are my three. So now I get to write integral 1 to infinity 1 over x dx. So we are now allowed to write the integral, and then we can now integrate. Remember that this is the limit. B goes to infinity. Integral 1 to b, x to the minus 1 dx. Limit b goes to infinity. The integral of, I don't know why I put it as 1 minus x. What is the integral of 1 over x? Very good. From 1 to b. And what do we have? We have the limit. B goes to infinity of ln b minus ln 1. How much is ln 1? 0. So what do I have? And what's ln of infinity? Infinity, right? Because as you can see, the graph, right? It rises to the right all the time. Now, what do we say for improper integral? By the way, guys, this question that I just did, this is your question on the test next week, right? Because I just did type 1 improper integral. This is your 8.7 or 8.8? What was it?
8.9.
Right?
There are many eights. Many eights.
But this is, right? So what I just did is the improper integral type 1. Now, what do you, what kind of conclusions do we get from improper integrals? If it goes to a number, it converges. If it goes to infinity, diverges. Okay, so integral diverges. Are we done with the problem? No, because that you proved the divergence of the integral. No one cares about that. Your question was, what's happening with the series? Well, now you go back to the test, and it says that they share the same fate. So now you have to say, and here is the answer. Ready for the paragraph? Yes. Answer. Since all three conditions hold and integral 1 to infinity of 1 over x dx diverges, series 1 to infinity 1 over n diverges by integral test, by IT. That's the answer, that sentence. You cannot say, because guys, this D, the black D over here, is the divergence for the integral. And that's not the answer, right? The test is the answer. The test which says that they do the same thing. I know it's convoluted, but you'll get used to it, like everything else in life, right? It's just a new normal now. So now let's quickly look at the whole problem and then immediately do the next one. So I have a series. I transform the sequence into a function, continuous function f of x. I check the three conditions on f of x, make sure all three pass. And then, when they all pass, I go and I do the improper integral, which will converge or diverge. And once that is done, since 3 conditions passed and the integral either converges or diverges, we get to write the red answer and score points. So that this red answer, this sentence, that's 2 points out of 10, right? So why have a B if you can have an A, right? That's just, I mean. Now, what happens if one of the conditions fail?
Move on.
Yes, move on. A different test, right? Now, you will say, well, how do I know if I should do integral test? Well, the thing looks like you should be integrating, right? 1 over n you can integrate, and then if you can spot the substitution, right? U sub, you can spot partial fraction decomposition. Well, you might be lucky and have telescoping, right? So you don't have to go through this nightmare of these proofs and things like that. Yes.
Is there a certain order we should be doing tests other than?
Oh yes, and that's going to be the lecture once I cover all 10. We are going to have the order, and the order will say divergence first. I already started that order for you. So divergence first, geometric. It's technically the order of the sheet. It's the order of this sheet.
Okay.
And that's the reason why I am not copying the one that it's in your book. Your book has this, and you see that the order of sections is not the same as the order in the book. But yeah, because this is the order in which you should be going down the line and asking yourselves, right? Is it this? Is it this? Is it this?
You never do direct comparison, right? That's what I was told.
It's a last resort.
Okay.
Just like you don't really want to do quadratic formula if you can factor, because it's just so computational intensive that most likely we're going to screw it up, right? So direct comparison is going to be the last resort, and if everything else fails, well, you have no options, right? Then you have to do it.
Okay. I'll do it. That's what I was told to skip that problem. It's like honestly, everything else fails.
If everything else fails, fail the problem.
Yeah.
That's what you gotta do things.
Yeah, told me that. Dan told me not to do it.
That's what that means.
Ready for the next one? Summation 1 to infinity of 1 over n squared. All right, so 1 over n diverges. Shall we try and test the common sense on this one? No, we learned better, right? We're just going to leave it be and do the test. Okay, now, if we so an is 1 over n squared. F of x is 1 over x squared. Now, you might know the graph for this. So is it continuous on 1 to infinity? Yes, it is, because as you can see, right, we just have this part from 1 to infinity. So it looks exactly the same as 1 over x. So yes. Number 2, is it positive on 1 to infinity? The answer is again yes. And number 3, is it decreasing on 1 to infinity? And the answer is yes. All right, all 3 passed. Let's do the integral. Now I get 1 over x squared dx. It's a limit b goes to infinity, integral x to the negative 2 dx from 1 to b. That's the limit b goes to infinity of x to the negative 1 over negative 1, calculated from 1 to b. Now this is just negative 1 over x, right? So we have limit b goes to infinity of negative 1 over x from 1 to b. Just to fix that a little bit, limit b goes to infinity of negative 1 over b plus 1 over 1. How much is the 1 over infinity? 0. So the first one goes to 0. And the answer is 1. Again, this particular integral is the problem for your exam next week, right? It's a type 1 improper integral. We haven't learned anything new there. Now, what is the conclusion of the improper integral when it's equal to 1?
Say that.
Converges. And now, it's time to write the answer for our series problem. Since 3 conditions hold and integral 1 to infinity of 1 over x squared dx converges, the series summation 1 over n squared 1 to infinity converges by integral test. Now to say this I have to stand up so I'm taller and more menacing. Your integral converges to what? 1. To 1. Your series converges to? We have no clue. Okay? So please do not say converges to 1 because they do not converge to the same value. Write it down, right? They do not converge to the same value. The only 2 tests where you know the sum are geometric and telescoping. That's it. So geometric and telescoping are the only 2 tests that you will know what it converges to. The rest, we have no clue. So you have 8 tests. Well, no, divergence tests can't show convergence. So the 7 tests, you will be writing converges, and you have no clue what it converges to, including integral test. Fair? Good. Ready for the P series, and then next class we'll do more integral tests because we need spicier examples with harder integration and then worse situations for proofs, right? Because right now we have 2 basic functions. You just look at it and you know, right? What are you going to do when you have a polynomial divided by polynomial? Are you going to crank the entire 2-page to draw a graph? No, right? So, yeah, you could. So we'll do more integral tests next class. And next class we also need to do the review, right? And then there is exam, and then we do the next. I think comparison tests are next. Or maybe, yeah, comparison tests are next. Or Rouge, something. Anyway, P series. Oh, yeah. Oh, yeah. Easy. P series. What's the test for P series? So, you look at the P, just like you look at the R for geometric, now you're going to look at the P. That's it. So what do I have? This is the form. Summation 1 to infinity, 1 over n to the p. P is the power. So now, if p is bigger than 1, we have convergence. If p is less equal than 1, it's divergent. Done. Let's do 2 examples. Summation 1 to infinity of 1 over n. Remember how we did the integral for the entire page? Well, what's p for this one? 1. And what do we know if p is equal to 1? Diverges. Great. 1 over n squared. That's our second integral test we did. What's p? 2. And that is greater than 1, so by the test above, converges by p series. I know, it's the same like geometric. Now, please tell me if you don't memorize the p series test, right? You're just dead in the water, right? Can't do anything. I mean, you can guess, it's 50-50 chance, right? But do you take the chances? Now, do p series eliminate integral test? No, not by far. P series are just this little tiny special case, right? Where you get your 1 over n to the 10, 1 over n to the half, right? If you, what's a series of 1 over root n? 1 over root n. Why? Because p is equal to a half, less than 1, right? So see, it's a narrow set of problems that you can do, but this is going to shine with the direct and limit comparison, this test. Because we're going to get some really nasty series, right? And then you compare them to p series, and then it's, oh, immediately. It's nice, right? So, these 3 tests, like 10.4, none of them gives us convergence to a number. And the rest of the tests, the other 5 tests that we didn't cover, they won't either give us convergence to a number. Divergence test can only show divergence, and as I said, you should check that problem. You should check that first for every single problem. We also saw it. We were also seeing that 3 to the n, which is geometric problem, was faster with maybe the same. But 3 to the n, right? Limit of 3 to the n is infinity, diverges, or 3 is bigger than 1, diverges, right? It's the same, right? It's not too much work either way. And then we saw the definition for E. Now, I did ask you guys to review L'Hopital's rule from Calc 1. If you don't know this definition for E from Calc 1, and we also did this in chapter, I believe, 7, this definition, right, is just going to get more complicated, because you're going to have 1 plus 3 over n, or 1 plus 7 over n. 1 plus 7 to the n raised to the 2n, right? Well, that's e to the 14. And you go, oh, e to the 14? Yes, right? Because whatever number is here times whatever number is in front of the n over here, you multiply those two to get the power of e. Now, how do I know that? I did 5,000 problems, right? Are you going to know this? Well, if you do 5,000 problems, you will. But to prove this, you have to use L'Hopital rule to prove this E problem. And then we have our integral test, right, which goes on and checks this rule. So next class, we are going to do 2 or 3 examples of integral tests. That's going to take time, maybe even an hour, to do those 3 problems, because we have to actually do the proofs now. We can't do, right? We have to do the proofs. And then, when we're done, right, we'll do the review, and then on Thursday is the test. Bye.